Hey everybody, it's your favorite science teacher. I'm not here today, but I should be back Wednesday. And so I wanted to go over, I didn't want to waste this day on the content. And so we want to make sure we learn some of the content here today. We're going over covalent bonds, and we're starting covalent bonds and working on that. And so that's what we're starting with here. So let me share my screen. Okay. All right. So let me see here. All right. There's that preview. All right. All right. So what we're doing is again, we're first off, before we get to those, we are going to finish up some of the ionic bonds. And so right here are our standards that we're learning today. Explain what hydrides are and give an example of one and properly name them. Explain what hydrates are, give an example of one and properly name them. Explain what covalent compounds are and why they form. Explain what a molecule is and give examples on, and correctly draw Lewis dot structures and explain how to draw Lewis dot structures. Explain how to draw Lewis dot structures. All right, and so that's what we're learning here today. All right, and so let's look at that right now. All right, so starting off is we're covering over hydrides. Okay, hydrides. We said ionic bonds. What is an ionic bond? It's always between what and what? Yeah, if you said metal and non-metal, that's correct. Okay, and a hydride is where the non-metal is hydrogen. Okay, hydrogen can be a non-metal that accepts an electron and it becomes an anion. And so it can do that. And so some examples are you can see lithium hydride, okay, magnesium hydride, and sodium hydride. And so it has a higher electron affinity and ionization energy than the metals. And so they will gain the electron. And so why does it happen? Again, because again, the anion, and so let me write this over here real quick. Let me go camera. Pause the video for a quick second. All right. And so what happens is, like, for instance, the example of lithium hydride. Okay. Lithium hydride. Okay. Lithium has a lower electronegativity and has a lower ionization energy. And so if we remember, lithium will have that one valence electron. This is the before. Hydrogen has that one valence electron. All right, this is the before. And so what will happen is that lithium, since it has such a low ionization energy, um, it's going to lose that electron easily and give it to hydrogen. And hydrogen is now going to have a negative. This can be the after. I have two electrons, and it's got a negative one charge. And lithium is going to have a positive one charge. All right, those ions will attract, and this is called lithium hydride. Okay, and so this is how that works. All right, and so again, this is the anion, this is the cation. That's what we mean by hydride. Some of you are looking at it and say, hey, how can you deal with two elements that are in group one? Well, hydrogen is that one element. Uh, Remember, its energy level, it only has one electron. And it can gain, if that first energy level becomes full, if it gains one more electron, and if it gains that electron, now hydrogen has the electron configuration of helium. And so it has the electron configuration of helium, and lithium has the electron configuration of helium. It's just they have opposite charges and they attract. And so that makes them stable. And so these are hydrides, right? It's a type of ionic bond that we didn't have time to go over, but we are going over right now here. All right. And so the next thing here, all right, hydrates. All right. Let's go over what a hydrate is. And we actually ran into hydrates. I think one of my groups, I think maybe in seventh period, got to deal with a hydrate. A hydrate, a chemical compound containing water that is chemically combined with a substance and can usually be expelled without changing the constitution of the substance. All right, let me pause this for again. So again, we're talking about hydrates. Hydrates are ionic compounds that are combined with water in part of their crystalline structure and their lattice structure. And they can be removed if you heat them up. In fact, we did this the other day with, again, seventh period. Seventh period, one group ran out of magnesium sulfate. And I grabbed some magnesium sulfate from my room, but I didn't grab magnesium sulfate. I grabbed magnesium sulfate heptahydrate. And magnesium heptahydrate has water inside its structure. So when they heated it up, the water came out of the structure and turned into a liquid. And so it melted very quickly, and it wasn't supposed to melt. The magnesium sulfate was supposed to not melt because it wasn't supposed to have any water in part of its structure. And so it was kind of like this structure right here. And so let me show you what I mean by that right quick here. All right, exit full screen. Here we go. And so it was magnesium sulfate is MgSO4, but we wrote a times 7H2O. It's called heptahydrate, magnesium sulfate heptahydrate. And it's kind of and here's again what we're talking about with this. You can kind of see it right here. Magnesium sulfate heptahydrate, cobalt 2 chloride hexahydrate. Again, that means that water has been made into its structure. Here's a picture of this. I was looking it up and I was like, oh, they need to see this. This would be cool to see. All right. And so here are some of the different structures. I believe this is anhydrous. Anhydrous version of this. And again, this is magnesium sulfate heptahydrate. And this is actually right here. And you can kind of see it right here. It's a little bit more crystally and stuff. If we are looking at anhydrous magnesium sulfate, all right, this is what it's going to look like here. It's going to look more powdery. It's not going to look more crystally. It's going to look more powdery. All right. That's what it's going to kind of look like. And so it's going to be a little bit different structure. But again, these are called hydrates. Okay. And so I wanted you to see that so you can kind of understand it. And the way we name them is you use these prefixes. We don't usually use prefixes with ionic compounds, but when we do hydrates, we do. All right, so this would be lithium sulfate dihydrate. All right, this would be calcium bromide tetrahydrate. All right, so this is again how you do that with that. Okay, now we're shifting to covalent bonds. All right, covalent bonds. All right, what are covalent bonds? They are again a bond, a force that holds atoms together, typically between two nonmetals, and they share their valence electrons. And again, when we have any type of chemical bond, it's always a force that holds the atoms together, and it helps them act as a unit. Uh, they act as a unit. That's a chemical bond. And we've done ionic bonds. In ionic bonds, what did they do? The atoms that are involved in an ionic bond, they did what? Did they share or did they transfer electrons? Yeah, if you said transfer, you're correct. They transferred electrons where one gained the electron, get a negative charge, and the other one lost electron, became a positive charge. And we went over that. That's what our test was on. Now we're shifting to covalent bonds, and we're going to go a little bit more deeper into it. All right. Covalent bonds share electrons so they can be stable. Okay. They can be stable. And those shared electrons are attracted to both nuclei, and that holds the atom together. Um, all right, let me pause the video for a quick second. All right, and so the trends that need to be taken into account for covalent bonds here. All right, and so let me see if I can do this. All right, some of the trends that need to be taken into account. First off, is that the elements that do covalent bonds are all nonmetals. They tend to be nonmetals in nature. Tend to be nonmetals in nature here. Covalent bonds are the ones that are going to do covalent bonds are always typically nonmetals. Right. Another tendency is that their electronegativities are a little bit closer in value. Their electronegativities are closer in values. That means they have equal pull on those electrons. They both want the electrons somewhat to some degree. And so therefore, they're going to have more equal pull, so they're going to share them. Where with ionic compounds, one wants the electron, the other one doesn't. So that means they transfer, are closer in value, more likely to share. And they also have usually higher numbers of valence electrons, usually higher numbers of valence electrons. So those are what a covalent bond is going to do here, okay? And so an example is CH4. That's called methane. All right. And again, covalent bonds are considered lower energy than atoms staying apart. And this is a classic diagram. This diagram right here is a beautiful diagram about this. It shows that the two atoms that are nonmetals, like hydrogen and hydrogen, require more energy to be apart than when they are bonded together and sharing these electrons. Not when they're super close, overpass, and they're forced to be overlapping each other. But when they are sharing these electrons, that makes their energy lower. All right. And that just kind of just shows, hey, chemical bonds are lower energy. And so therefore, that's why atoms form these chemical bonds instead of staying separate. All right. And so that's what this is trying to show right here. I don't really want to go into the naming covalent compounds and acids right here. We're going to go on to, we will get to that. We will get to that. We're going to go to the octet rule here. Atoms that undergo bonding in order to satisfy the octet rule, they all want to be this noble gas-like. And again, that's kind of just like ionic compounds. They're trying to become stable. Okay, they're trying to become stable and become noble gas-like by sharing those valence electrons. And so I'm going to show you one of these real quick here. All right, and so what we're going to show right here is I was going to show you is how to do what some of these Lewis dot structures in just a second, and why these are covalent compounds here. So our, for instance, is the diatomic molecule called F2. Okay, if we were doing F2 before F2 actually bonds together, it would be it'd be they have 7 valence electrons. That's not right there. All right, they have 7 valence electrons. Right? And this is what we considered again high energy. Remember the how fluorine has that high electron affinity. They really want to gain one more electron. They really want to gain one more electron. So what they're not gonna stay as atoms separated. They're going to join together here, and they're not going to transfer electrons. They're going to share. And so they're going to put one electron together and share with the others here. All right. All right. And that gives this fluorine on the left, if you count the unshared ones, that's 1, 2, 3, 4, 5, 6. All right. 7, 8. That's 8 valent. That's 8 electrons if you count the shared ones and the unshared ones. And if you count the shared ones and the unshared ones here, it's also 8. That makes them have a neon. Both of them have that neon gas or notation, that neon gas notation. All right, since they both have that now because of them sharing those valence electrons, it gives them some stability. All right, instead of them being separate, which makes them high energy. Okay, um, so we've gotten that right here. And so we're going to learn how to do these, what we call these dot structures, Lewis dot structures. Again, this is high energy, and this is what they do after. And these are called Lewis dot structures. We did them before with ionic compounds, but if you remember with ionic, one would transfer one to the other, and one would become a negative charge, and the other one would become a positive charge. But that doesn't happen with these. That was with like sodium and chlorine. All right. All right. We did that, and they became ions. That's an ionic compound. But with covalent, they're going to share. All right. And they're going to share. And we represent the shared electrons with a dash. Anytime we see a dash, that's a shared pair of electrons. Okay. And so that's a covalent compound if we see a dash. All right. And so going back over here. All right. And there are some elements that are going to be exceptions to the octet rule. Hydrogen is one. Um, it forms only one bond and has 2 valence electrons at first level. Remember, becomes hydrogen doesn't need to get 8. It just needs one more to have helium's electron configuration. So it's going to share with something that'll make it have the duet rule. Boron has 3 valence electrons. It tends to form 3 bonds, and it doesn't actually get the 8 valence electrons. And some can have what we call the expanded octet, and and then which makes them highly electronegative atoms. Expanded octet involves empty d orbitals to fit the extra electrons, like SF6. It would sulfur would share an electron with fluorine on sulfur would be the center and share one electron with each of these. But that would make now sulfur to have 12 electrons if you count all those electrons. And so that would be a lot of electrons. And so that's not, that gives it a lot of electrons. That's an exception to that octet rule. And it puts it in that layer here. All right, so we're going to do these Lewis dot structures. I just did one, and so it's your turn to do some here. A formula where the atomic symbol represents the nuclei and the inner. I didn't mean to do that. And the inner shell electrons. That's what the symbol represents. And the dot represents the valence and the bonded electrons. What are they used for? It gives us to visualize bonding of atoms, represents where electrons are locating, and gives relative bond strengths and established reactivity of models. All right, there are steps to do this. Okay, determine the types of atoms in the molecule, CH3, I. So you write down the molecules, the formula of the molecule, that's right here. Then write the electron dot notation for each atom. That's like usually the before. Then determine which of the atoms, the total number of valence electrons. And so, like for instance, this compound right here would have 4, 3, and this would be 7 valence electrons. And so we're going to do this one real quick here. I'm going to probably do this one. Give me 1 second here. Let me do it this way here. All right. So again, you're going to put the least electronegative atom in the center, with exception of hydrogen. Hydrogen is never going to be in the center. And place at least place one shared pair of electrons between each of the atoms. Fill in the valence electrons with the unshared pairs and count the electrons to make sure all valence electrons are accounted for. All right. I think we can do that first one here. All right. Let's do the one right over here. Let's see. So again, we've done that right here. So you wrote that you're going to do this, and we're going to walk that through here. So I'm going to show you this on right here. So we're doing CH3I. All right, and it says do our dot diagram before we do each of them here. So carbon has got 4. Hydrogen, we got 3. All right, and iodine has got 7. Okay. And so those are all our dot diagrams. Then we count how many valence electrons it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 valence electrons. Okay. So with 14 valence electrons, I'm going to typically put the element that is the least electronegative. Now, carbon and iodine both have an electronegativity of 2.5. But from experience, I know that I'm going to put carbon in the middle. You would figure this out eventually here. All right. And so I'm going to put carbon in the middle. And it says you're going to put 1 pair of electrons between each of the atoms. And so you want to have with the central atom. Okay. And that gives me, if I do all that, that gives me 8 electrons that are being shared out of those. I have 6 valence electrons left. Hydrogen now has a noble gas configuration of helium. That's 2. All right, every hydrogen is 2 valence electrons. Carbon is now met its octet rule. It's got 2, 2, 2, 2. That gives it 8. Iodine, I have only got 2 for it, but I have 6 electrons that are still left. So I'm going to put all those 6 right around iodine. And that gives iodine, 6 valence electrons that are lone pairs, and it gives it 2 that are shared pairs and stuff. And I could rewrite this here when I could draw it like this instead. And then have the lone pairs like this. Okay. And so that's the same thing. Anytime I write a dash, that's the same as a shared pair of electrons. Let's do one of these here. Let's do another one. And let's go back and show you. We're going to do one of these here. All right. It's your turn to do this next one here. And we're going to do NH3. All right. Write NH3. All right. And we want to do the same thing we did on the last time. And so here is what we did last time. You can kind of look at what we did last time. We wrote the symbol. We wrote it out. NH3. All right. And then I'm going to do if you remember, the dots, diagrams for each of the elements by itself, then count the total number of valence electrons. And then I put the element that has the lowest electronegativity in the center, but I definitely don't put hydrogen. So I'm going to put everything around the nitrogen here. All right. So do that. I'm going to pause it for a second, see if you can figure it out. All right. It's now time to see what you got. All right. Nitrogen has 5 valence electrons. Hydrogen has 3 valence electrons. This is all before. How many total valence electrons is that? 1, 2, 3. That's 8 total valence electrons. All right, and so what I'm going to do is I'm going to do nitrogen bonded to a hydrogen, bonded to another hydrogen, and bonded to another hydrogen. All right, that makes all those hydrogens have a noble gas configuration of helium because they have 2 valence electrons, 2, 2, and 2. The nitrogen has only got 6 electrons right now, valence electrons. So it's not meeting the octet, but I've used only 6 of my 8, so I have 2 left. And so that means I'm gonna put those last 2 around nitrogen. This is called ammonia. And so this is, again, what ammonia would look like right here, right? And so that's what we want. And that's the after structure. Let's do another one. Now, again, when we do this next one, I want the teacher to pause the video for a quick second, for about 1 minute, and you're going to do H2S. All right, H2S. And I'm going to come around and check and see if you get, just after 1 minute, try to do it. And then she's going to start the video again in 1 minute. All right, so back right here. So you had hydrogen, you had 2 hydrogens, and you had sulfur, which has 6 valence electrons. That's a total of 8 valence electrons. All right, and so since that's 8 valence electrons, you're going to put sulfur in the middle because, again, we don't ever put hydrogen in the middle with these. All right, and we draw one bond that shows that's a pair of electrons shared with each of these hydrogens. Each of the hydrogens are now stable. They got a helium electron configuration. And that takes 4 of those 8 valence electrons away. I still have 4 more. Those last 4 will need to go around sulfur. So sulfur will now have 8 valence electrons. And now it's got neon's electron configuration. And so this makes this compound is called dihydrogen sulfide. Dihydrogen sulfide is notorious for giving a rotten egg smell. It's produced by paper mills and stuff. So it's dihydrogen sulfide. Okay. Do another one. All right. 1 minute. All right. We're going to do the next one. The next one is, there it is. SiH4. SiH4. And so I'm going to give you 1 minute to do SiH4. And if the teacher will pause the video, and then after 1 minute, resume it. All right. So back at it, here is the answer. It's SiH4. All right. And silicon, it's silicon with 4 valence electrons, hydrogen each with 1 valence electron. and we draw silicon in the middle. We draw a bond to every one of them. And that gives, again, hydrogen's now stable. Silicon's got that meets the octet rule. And if we can't subtract from our total number of valence electrons, we get 0. All right. And so we get the picture of how to do this. All right. Let's see what we have next here. All right. Now we're going to switch it up to for O2. Okay. O2 is one. This is probably the last one we're going to do today. O2. Okay. O2 is what we breathe. When you take your next breath, that air that you just breathed was mostly nitrogen, but the part that's useful to your body is the O2. All right. And so we want to draw the structure of O2. All right. And so O2, if we did the before, it has got 6 valence electrons, both of them. And that gives a total of 12 valence electrons. Okay. All right. And so we really can't do any one in the middle. So I'm just going to do oxygen and oxygen and then bond them together. All right. Let's see if that works here. All right. All right. That takes 2 of my electrons away. So I've used 2. So I have 10 left. All right. Of my 12, I'm going to put the remainder around here. So I'm going to give this one, I need to have 8. So I can meet the octet rule. All right, that gives this one 8, but I've used 6, so I only have 4 left. So that's not going to work because that gives this one only 6. It's not going to meet the octet rule. All right, and so we want to try it again. So this is called a trial and error process. So this one's not going to work. Let's try it with, instead of just a single bond, let's try it with a double bond. Okay. And it's not sharing 1 pair of electrons, it's sharing 2 pairs of electrons. All right. And so when I do that, I got 12 valence electrons minus 4. That gives it 8. And this side gets 2 lone pairs that are not shared. And this side gets 2 lone pairs that are not shared. And that gives it 8. And this would work. So this is the structure of O2, that oxygen that we so desperately need. And so this is the structure of O2, and it's a covalent bond. It shares those valence electrons. What I'm going to have you do now the notes are through for today. You're going to do some of these practice problems here, okay? You're going to do some of these practice problems and draw the Lewis structure, and I'll write the name on some of these things out, and then I'm going to have you do that, all right? And that's the classwork /homework, all right? All right, have a good day.